3.4, applying Pascal's triangle. Pascal's triangle can be applied when counting paths and routes. So what we do is we label the starting positions, node, and node is just like, see down here, just like the points here of like intersection, okay, with a 1. Okay, that's going to mimic row 0, entry 0. And then what we're going to do is we're going to move along the outside, labeling all the other nodes with a 1. Okay, that's only the outside though. And then we're going to start to fill in the middle as we would Pascal's triangle. Okay, and then just know when we fill in the middle, only add numbers where there are 2 routes going into a node. So, example 1, counting the number of routes, assuming that you only travel south and east. So, south and east. So there's no backtracking. How many paths are there from A to B? So we're going to start here, A, 1. So to get from this point to this point, 1, because we can't travel down and then back up. So therefore, all of the nodes across going east are going to be 1. And then all of the nodes going south are also going to be 1 because we can't travel out here somewhere and then travel back. So there's no way of getting back to that beginning position. Okay, and now this node here, we're going to add 1 and 1, which is 2. This node here, we're going to add 2 and 1, which is 3. We're going to write it right on the node. 3 and 1, which is 4. 4 and 1 is 5, 6, 7. So that one's quite easy because we're adding 1s every single time. And then it gets a little bit more difficult. 1 and 2 is 3. 3 and 3 is 6. 6 and 4 is 10. 10 and 5 is 15. 15 and 6 is 21. 21 and 7 is 28. Okay, and then we keep going. 1 and 3 is 4. 4 and 6 is 10. 10 and 10 is 20. 20 and 15 is 35. 35 and 21 is 56. 56 and 28 is 84. And then finally, the bottom row, 5, 15, 35, 70. 70 and 56 is 126. And then add our 84. So here, therefore, the number of routes is 210. Okay, if we take a look here, just as an example, let's talk about this number 3. Okay, here are the different routes going in here. So 1, 2, 3. Okay, and then if you think about 4, well, we have all 3 of those, plus we can go in this way. Sorry, we can go in this way. So 1, 2, 3, 4. Okay, and so on. So each time we count a node, what we're doing is we're labeling how many ways can we get to that node. Okay, random node, there's 20 ways to get to this node. There's 4 ways to get to this node, and so on. And that's why we add them up. And then we read this last one. So there's 210 ways to get to B. Okay, so again, assuming that you can only travel south and east, how many paths are there from A to C if you stop at B on the way? So we actually have to go from A to B and then from B to C. So let's do this one first, A to B. So 1, 1, 1. I'm not going to label these here because, again, we can't travel past B and then go back to B. Okay, and then we're going to go 1, 1, 1 down the side, but I'm not going to label these ones because, again, we can't go down and then back to B. Okay, so now let's add these. 1 and 1 is 2, 2 and 1 is 3. 1 and 2 is 3, 3 and 3 is 6. 1 and 3 is 4, 4 and 6 is 10. So we are going to have 10 different ways to get from A to B. Okay, now we kind of restart at B. going over, these are all going to be labeled 10. And going down, also labeled 10. Because once we have a 10 here, it's it's as though we're starting back at like the beginning of Pascal's triangle with the 1, but this time we're starting with the 10. Because we know that we're starting at 10 roots at B. And then it's going to be 20, 30, 40, and then 50. So the number of roots from A to C when stopping at B is 50. Okay, counting paths in an array. So how many different paths can we spell Pascal? If we started at the top, call this paths, and proceeded down to the next row by moving diagonally, like either right or left. Okay, so we're moving down the whole time. So let's blow this up. Okay, we're going to start with the P. I'm going to label P1. And going down, just like Pascal's triangle, we're going to label everything on the left and the right of the diagonals 1s. And now let's fill in the middle. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 and 3 is 6. 3 and 1 is 4. 4 and 6 is 10. 6 and 4 is 10. So, in order to get from P to either one of these L's, there's actually going to be 20 roots. Okay, counting paths on a checkerboard. So assume you can only travel diagonally and upward. So on a checkerboard, you can travel diagonally and upward, okay? But you can travel diagonally from any spot that you're in. So essentially, we're going to only land on the white spots, but we can't go backwards. So these ones are out of options. How many ways can the checker reach the opposite side of the checkerboard? And just note, we can't pass through X. So let's clean this up. I'm going to go red. Okay, so 1 down the diagonals. 1 down the diagonals. Now let's add. 1 and 1 is 2. 1 and 2 is 3. 2 and 1 is 3. Those are all easy ones because we can add 2 numbers. 1 and 3 is 4. 3 and 1 is 4. Those are easy. We just add the 2 numbers. We don't need a number here. Okay, 1 and 4 is 5. Here's the thing. This is technically 4 and 0. If you think about us not being able to get to this, there are 0 paths to get to that X. So we continue with a 4, just kind of like we do down the side of the triangle. Okay, again, 0 and 4 is again 4. And now 4, it's kind of like we're putting a 0 here. 0 and 4, because we can't get off the checkerboard. So 4 and 0 is 4. Okay. 5 and essentially 0 is 5. 5 and 4 is 9. 4 and 4 is 8. 4 and 4 is 8. So the number of paths that you can take to the other side of the checkerboard, we have to add these together because there are 5 ways to get to this position, 9 ways to get to this position, 8 ways, and 8 ways. But altogether, it would be all of these added up, which is 30 different routes to get to the other side of the checkerboard. Okay, now, same style of question. Assume you can only travel diagonally and upwards. How many ways can the checker reach the opposite side of the checkerboard if you cannot pass through? Again, the red squares. So we're going to assume these red squares are 0. We cannot pass through. So we can go ahead and write zeros on those. So let's just practice. 1, 1, 1, 1. Okay, those are all of our diagonals. Now 1 and 1 is 2. 1 and 2 is 3. 2 and 1 is 3. Easy. This one floods into this. Again, you can think of it like you can't go off the checkerboard. So 0 and 3 is 3. we're not going to add these two because we can't land here. And then 3 and 0 is 3. This branches out just like the side of the triangle. Essentially, you can think of it as, well, since we can't land here, we can't land here, 3 plus 0. We can't land here, we can't land here, 3 plus 0. You can think of it either way. Now, 3 and 0 is 3, 0 and 3 is 3. Lots of 3's here. That ends with a 3, that's a 6, and that's a 6. So the number of roots is going to be the 3 plus 6 plus 6 plus 3. Right? There's 3 ways to land here, 6 to land here, 6 to land here, 3 to land there. So there are 18 different roots to the other side of the checkerboard.